right, cool guys. Now what you're going to see today is it's still a review, but let me tell you, it's stuff that was probably hard for you when you were in Algebra 1. Then you didn't see it last year much at all, if at all. And so this year it's going to come back with a vengeance, and your teacher's going to want you to be good at it, but you're going to be like, it's been 2 years and we're a little rusty. So that's the point of this, is to hopefully you're not rusty and you'll be, you'll be the best ones at this. You'll remember a lot of good stuff. So inequalities and systems of equations. Now, an inequality would be like an equation, except in an equation you're equal to something. Inequalities were those things where instead of an equals, you had less than, or you had greater than, or maybe you had less than or equal to, or greater than or equal to. So I'm going to put a little key up in the corner, and the reason for that is because we're going to talk about, when you see these, the differences on how it will look graphically, which a lot of this today is the graphical solution if you see these symbols. So if you're on a number line and you see greater than or less than, what's going to happen here, let me switch colors, is less than would be an open circle because you don't actually get to include it, and then less than means that it's going to be solutions that are headed that way. Greater than would still be an open circle, but now it'll be the solutions to the right. Less than or equal to would be a filled in circle, also heading left, and then a filled in circle heading to the right. So hopefully that makes sense. If you're less than or equal to, you get to include the number, or you get to land on the number, and therefore it's a filled in circle. Whereas up here, we call that a hole in math, like H-O-L-E, hole, because you don't get to include it, you skip over it, you don't technically land on it. Okay, so that's what it'll look like on a number line. Now, we're not done with our key because we also need to talk about what if you're on a coordinate plane. And if you're on a coordinate plane, what this means is that if you are less than or greater than, you need to really keep in mind that it will be a dotted line. Now, it may be slanted this way, it may be slanted that way, it may be vertical. I don't know what it's going to look like, but it needs to be a dotted line on a coordinate plane, whereas this one gets to be a solid line. Okay, so keep those in mind, and then there's going to be some shading involved, which we will talk about as we do the problems. All right, so let's do solutions on a number line. So what do I mean by that? Well, what I'm talking about here is a problem that maybe starts out like, let me go back to green. Okay, maybe it's just like we did last week, where it's like 3 times x plus 1, and then it's greater than 5x plus 10. Okay, something like that. Okay, so if this happens to you and you're supposed to be solving it, that was weird, I lost part of my 5. If you're supposed to be solving this, you kind of do it just like you did last week, right? You start by distributing, distribute. So 3x plus 3 greater than 5x plus 10, and you're trying to get the x's together, so you might subtract 5x from both sides, and then you would subtract the 3 over, so it would look something like this. And I didn't show all my work, but it's because I want some room to groove. Here's the kicker that most people forget. At this point in the problem, you have to divide off the -2, right? Well, when you divide by a negative, you must flip the sign in the middle. Okay, so let's make a note of that. If we divide by a negative, and that's always on inequalities, divide by negative. If so, flip the sign. It's the only time you flip the sign in the middle is when you're dividing by a negative. So what that'll mean is your answer will be x is less than -7/2. And some teachers are okay with, like, this is your answer, yay. Some people want it on a number line. I like to see the answer on a number line. Let me put 0 on there. -7/2, where would that be? So -7/2 would be like -1, 2, 3.5. And what we're going to do is the same thing that we did up there. If it's strictly less than, then we need to be thinking about that one, okay? So I'm going to put an open circle at 7/2, and then I'm going to shade to the left. And that would be x less than -7/2, okay? If you're on a coordinate plane, all that this means is instead of solving for one variable, you might have something like 2x minus y is greater than or equal to 4. Okay, so if this was your problem, you're going to be graphing it in the xy plane. Let me kind of put that down here. So you would have a little bit of work to do first. To graph this, you might want to get it into slope-intercept form. So I'm going to start by moving my 2x to the other side. And now the y is a negative. You want that y to be positive. So you're going to divide everybody by -1. Well, guess what? I'm dividing by a negative, everybody. So that should tell you that we need to be careful and we need to flip that sign in the middle. I'll go back to my green for funsies. Okay, so divide by -1, divide by -1, divide by -1. Okay, so everybody got divided and it flipped the sign in the middle. Now we graph this like we normally know how to graph. Now, will I use a dashed line or will I use a solid line? Well, look up at your key. We are supposed to use a solid line because this is less than or equal to. So I'm going to start at -4. 1, 2, 3, 4. I'm going to put a dot, point, and then up 2 over 1, up 2 over 1, and I'm going to draw my solid line through those. And on these, it's not only dashed or solid, but you also have to decide where to shade the graph. Now, this says y is less than or equal to this line. Well, if you think about being less than something, and you're on this kind of a two-dimensional graph, less than something, hopefully it makes sense that it means under it. Like if I'm less than, I would think I need to go to the bottom of the screen because I'm small. And so the shading is going to occur below the line. Okay? If that had been greater than, think big numbers or above and you would be shading up there. But this would be the solution. So it's not just the line. You better do that shading or the teacher will not be happy with you. Okay, so that's the first main idea in this video, is just graphing with inequalities, either number line or coordinate plane. And I'm also going to scrunch into this same video how to do systems of equations, okay? And I'm going to go fast, so you may need to pause, rewind, all that good stuff, but I'm going to do all three methods as a refresher, okay? A system of equations is when you have two equations and two unknowns, and the goal is to find the xy. So what is the solution, the x and the y value that make both of these equations true? That would be the goal. And if you're using a graphing technique, you do exactly that. You start by graphing. So the first one is already in slope-intercept form. So what I'm going to do is graph the line 3x plus 1. So it starts at 1, and then it's up 3 over 1. This one I wish I had a good grid on. You may want to take time and draw an actual decent grid. So up 3, 1, 2, 3 over 1, and then I'll just do a down 3 left. 1, 2, 3, left 1. Okay, so here is the first line, and on the second one we want to graph this one as well, but notice it's in a crappy form. So what you want to do is do a little bit of work on getting the y by itself. So let's see, divide by -2 would mean 1/2 x, divide by -2 minus 4. So 1, 2, 3, 4. And so if it's a, let's see, then it's up 1 over 2, up 1 over 2. Okay, so somewhere down there they are going to intersect. Now, this is exactly why I don't like this method. Sometimes you do all this work and then you're like, oh wait, the graphs haven't intersected yet. Well, you got to keep going until you find out where they do intersect. So you know how this one we were going like down 3, left 1. You're going to need to go down 3 again and then left 1. And when you do that, you'll find where they intersect. And it looks like, according to my graph, let's see, I was at -2, so down another 3. 1, 2, 3. Puts me at -5 on the y. And my x value, I was at 0, and then I was at -1, so that would be like -2. Okay. From my picture, that's terrible, by the way, that's kind of what it looks like. So I would go up here and like check my answers by plugging them in to see if this even works. I do believe they work once you plug them in, but having either a grid would be beneficial or just not even using this method. Okay, this method is so time consuming. All right, substitution, that is most people's favorites. It's not mine, actually elimination is mine, but substitution, most people, their teachers spend like a year on it, and so they're really good at it, but they're, you still need a refresher. So how did substitution work? Well, substitution is a two-part process. The first thing is you need to isolate a variable in one equation. And then for part two, after you've isolated a variable in one of the equations, then you substitute the expression into the second equation. And then it just becomes, I'm not even going to write it, but then you just solve it, okay? So these are your two steps. Isolate a variable in one of the equations, then substitute that expression into the second equation. So what does that mean? Well, it means find one of these two equations and get one of the letters by themselves. Now, in equation 1, y is already by itself, so it's almost like that step's been done for me, which is awesome. And so if that's done, then we move on to step 2, which says to take the expression that it's equal to and plug it into the second equation. Well, where do we substitute it? Where do we plug it in? Well, this is the y, so I'm going to take all of that mess and plug it into y. So what that's going to look like is I recopy everything from equation 2, and instead of having a y right there, I put in whatever I'm subbing in from the other equation. So it is a substitution. Somebody goes out, somebody comes in. And from here, then we math it out. We're going to distribute the -2. And then we're going to, let's see, that's a -5x. I'm going to move that to the other side. So x is -2, okay? And then once you know that x is -2, you're not done. A lot of people think, oh yeah, I'm done. No, you still need y, everybody. So how are you going to find y? Well, you substitute again. It's called substitution for a reason. Now you substitute x back in wherever you want. Honestly, equation 1, equation 2, whatever makes your heart happy, plug that -2 back in. I'm going to choose the first one. And when I plug that -2 back in, I get -5. Oh, hey, look, that's the same answer as number 1. Why do you think that is? Well, I gave you the same problem. Don't know who noticed that, but now you're really going to notice when we move to elimination that it's the same problem again. I wanted to prove a point, right? You can use whatever method you want. It's just that sometimes one of the methods is better than the other. So let's move on to this last one. Elimination, my favorite. Okay, with elimination, all you have to do is line up the terms vertically. And I'm just going to put vert. I'm going to abbreviate because I'm lazy and I'm running out of room. So line up the terms vertically is step 1. And then you just want to add and subtract the equations with the goal being add and subtract so that something cancels. You want somebody to cancel. I think this is like super quick as long as people match up. And you'll see on this one it doesn't necessarily match, so we may have to do another step. So the first thing is line up the terms vertically. So what I'm going to do is bring the x's and y's to the left. And then I'm going to leave the whole numbers on the right. So my first equation would be y minus 3x equals 1. I'm just rearranging this equation, bringing the 3x over. My second equation, if I want to line them up, the x would go here, the minus 2y would be there, and then I'm still leaving the 8 right there. So I've lined them up. Now, if I try to add and subtract them right now, will somebody cancel? No, nobody cancels. That would be whatever. If you add them or subtract them, it's definitely not 0, which is what you want them to cancel out to. So one of the things with elimination is you can manipulate things. So for instance, like if I look at negative 2y and I'm thinking, ooh, if only that was a 2, then everybody would cancel. Or at least this would cancel. So I'm going to do that. I'm going to make this a 2. Well, if I make this a 2, I just multiplied that by 2. So make sure you multiply everybody else by 2. So hopefully you can see I'm just sort of writing over what I already had. Now we can add these guys together. That's going to make a 0y, which is what we wanted. We wanted that y to go away. A negative 6x plus an x is a negative 5x, and then over here we get a 10. So divide by negative 5, divide by negative 5, we get x is negative 2, just like we did on the other two problems. And this is also like the one from before. Once you get one of the variables, you've got to plug it in somewhere to find the other. Where does it get plugged in? Wherever you want. You could plug it into one of your new ones that you created. You can go way back. I usually go way back up to the beginning and just find the easiest place to plug it in. So I'm going to plug it into the first one and get y equals 3 times negative 2 plus 1, which is a negative 5. So hopefully that is a decent refresher on these three methods. And all that's left to talk about is the whole which method is best. Okay, when's the best time to use each method? And this is totally a personal preference thing, but what I'm going to do is sort of write my little notes under each of these as to when I use each one. And you can do, you know, whatever you want. I try to use elimination all the time because it's fast for me, but a really good time to use this one would be if you notice that one variable will cancel out immediately. And part of the challenge of this summer math program is reading my writing. My students always tell me that I should have been a doctor because that is the handwriting that I have. And I thought about it, and then I decided I'm too lazy to be a doctor. Okay, notice that one variable will cancel out immediately. So if that happens, like if above it had been like a positive y and a negative y, immediately right off the bat, then I totally would have used that method instead, okay? Now, when would I ever use substitution? Okay, I guess pretty much if it looks like above. If, meaning that, you know, it already had an isolated variable. Already had one variable isolated. So if that happens, then definitely use that. I usually don't ever use graphing, but teachers will tell you if both equations, both now has an E on it. Did you know that? Okay, let's try that again. Both equations are already, I can't think and talk apparently at the same time, already in y equals mx plus b form. That would be the only time I'd ever use graphing. If they both already look like that and I don't have to do a lot of work, then sure, maybe try graphing it out. This is not the best. This is not preferred, especially if these are fractions. You don't like ever want to use this. These two are going to be your favorites, and your teacher's favorites probably elimination. Most students like substitution, but use whatever you want, and good luck trying all the problems in the notes.